series about downhole gauges. Today, I have Juan Guerrero with me. Thanks for joining us today, Juan.
Thanks for having me.
Yeah, you bet. And so today we're going to continue that technical conversation that we've been doing monthly. This time we're going to talk about downhole gauges or live downhole gauges. Really the use of them, some of the background and the technical piece of it, and of course some optimization pieces when it comes to using that downhole gauge with artificial lift. And we're joined by Juan, our technical expert. He's our operations manager for digital solutions, which includes the downhole gauge.
Correct.
So we'll be able to rely on you quite a bit to go through the ins and outs of the gauge, how the gauge is applied, how we install it, how we acquire the data from the gauge, all the good stuff when it comes to actually running and utilizing this downhole gauge. And so today, really what we want to go over is the components that go into it, how you put the system together to get it ready to install. Of course, talk about the applications where we see gauges being run in some of the different business units, different operation basins here in the U.S., and also get some international input as well, where gauges are used and the types of artificial lift they're used.
Correct.
Of course, too, one of the pieces we'll talk about today is optimizing with a downhole gauge, different artificial lift methods, and how operators have historically used that gauge to optimize, if it's a rod pump or a PC pump or gas lift, different things like that. So glad you're joining us, and look forward to the conversation.
Thank you, sir.
Yeah, you bet. Of course, guys, just like our past conversations and trainings, if you have any questions, feel free to ask the questions via the chat function. We'll answer the questions as we go through the presentation. And then, of course, we can wrap up with any more Q&A at the end of our discussion here, Juan.
Perfect.
We'll also make sure that we record this presentation. We'll post it up on the Flowco website. So in case anybody has to get off early, or if anybody misses it, you can always come back and reference that training recording after we're done today.
Correct.
So, Juan, with that, you ready to get started?
Yes, sir. We're ready.
All right. Well, guys, we'll go ahead and get started. Have a couple things we want to talk about, just like our previous conversations. Get Juan's experience, Juan's knowledge. Juan's background has been focused on these live downhole gauges. He's really helped build out our training program, our operationals program, and also the equipment that we utilize too.
And the competency program for the gauges.
Yes, sir. Yeah. So all good stuff. And the idea with today's discussion is we're going to talk about all the components that go into it.
Yeah.
How you set up a system, what the gauge is doing, some of its limitations, both from pressure and temperature, and then kind of wrap up today's presentation and the optimization piece. How do you utilize that downhole gauge once it's there?
Correct.
So perfect. Well, Juan, let's go ahead and get started this morning.
Yeah.
So
we're going to talk a little bit about, of the Flowco Vision gauge, the specs, so everybody knows what we have here available.
Yeah.
Okay.
And so, Juan, when we talk about a gauge, this is basically a pressure transducer that we're installing downhole, right?
Yeah.
And this pressure transducer is collecting a couple different components, right? Of course, the big one's pressure, our downhole pressure. We'll call this our bottom hole pressure. This is usually going to be at the bottom or the end of a tubing string in most cases. So we're gathering that pressure information. Other things that we can gather, of course, are a temperature, so reservoir temperature, bottom hole temperature, and then also vibration, correct?
Yeah.
Okay.
Yeah.
And here, guys, we have a kind of an overview of the gauge itself. So I don't take up all Juan's time. This gauge that we see here and Juan's going to show us as well, is usually going to be at the end of the tubing string or as deep as possibly we can set it, so we can get that data that we're looking for: temperature, pressure, and vibration.
Correct.
So yeah, Juan, why don't you tell us a little bit about the gauge that we're going to discuss today?
Yeah, the gauge, our Vision Flowco gauge is rated to 10,000 psi, 150 C or 302 degrees F.
Okay.
It can measure vibration up to 18 Gs. Okay. Pressure resolution is 0.005%, which is equals to 0.05 psi. And the pressure accuracy, the published pressure accuracy that we have is plus minus 0.05% full scale.
Okay.
Which is 5 psi.
Biggest, that's 5 psi at 10,000 psi.
Correct.
Max pressure rating.
Correct. The diameter of the gauge is 0.75 inches, 3/4 of an inch. And the overall length of the gauge itself is just 10.5 inches. The base material that we use is 17-4 pH for the housing or the mechanicals, but also we have a version in Inconel 718 for sour service when required. All the seals that we use in the assembly are pressure testable, metal to metal.
Okay. And when you talk about the materials of the gauge, that's going to be important in like sour service wells, right? High CO2 or H2S, or really high chlorides with temperature, right?
Correct.
So picking that material based off of the corrosive environment of the well.
Yes, sir.
Okay.
Correct.
Perfect. And Juan, while we talk about the gauge, let's take a deeper look into the gauge itself here. So what we have is the gauge here that Juan's going to show us, and that's the component, right? That's the piece that we're installing downhole that it's going to register that pressure, temperature, and vibration.
Yeah, this is the Vision Flowco Vision gauge. Basically, this is the connection that interfaces with the gauge carrier. Okay, essentially. This section here, we screw this into the manual, and the gauge receives pressure through this port right here. Okay. This is the housing or main housing right here, and this is the connection that we have to make with the downhole cable using the cable head adapter. Okay. So that's pretty much what the gauge is.
So when you show this to us, Juan, the pressure from downhole, either tubing pressure or annular pressure, is going to be registered from this end there.
Correct.
Okay.
Correct. Now, our gauge carriers, they have all of them. They have communication internally to the tubing. So if we run the gauge carrier only, without the annular adapter, the gauge will sense the pressure inside the tubing.
Mm-hmm.
Okay. Now, we can use the same gauge carrier. I'm going ahead on myself here, but we can use the same gauge carrier using a little adapter, so we can plug up that, that hole right there with that adapter, and then it will have holes in the side, so we can actually sense the pressure in the annular port.
Okay, so for PC pump and rod pump and annular flow gas lift, you could register that tubing casing annular pressure with that. Okay,
correct.
Yeah, good. Thank you for sharing that. And guys, we'll jump back and forth because Juan was nice enough to bring some components with us, so we can kind of get a little more in-depth look at the equipment itself.
Yeah, perfect. Yeah, important to mention, we manufacture our Flowco gauge in our Flowco manufacturing plant here in Houston. It's a Flowco design, and we take care of the design, the manufacturing process, calibration process, calibration validation process. Everything is, supervised under Flowco. In addition to that, like I mentioned earlier, our pressure accuracy, or the published pressure accuracy, is 0.05% full scale. However, we can achieve 0.03% because the technique that we use to calibrate the gauges. In majority of the cases, we can get 0.03% full scale pressure accuracy, that's something that is not as usual to find in the market for this type of gauge.
That makes sense. And to clarify that, Juan, when you mentioned full scale, that's the max pressure of the gauge, right?
Yes.
So in this case, the gauge we're talking about is 10,000 PSI with a full scale accuracy of 0.05. So is that 5 PSI
5 plus
at
minus.
10,000 PSI?
Correct.
Okay. Yes, sir, Robert.
We have someone asking, what installations is this applicable for?
Oh, good question. Yeah, and so that's something we'll talk about here in a few slides. But the typical applications that we see with a live downhole gauge primarily is with artificial lift. So it would be to measure your pump intake pressure on a PC pump, which is a progressing cavity pump, or a sucker rod pump.
Yeah.
You can also monitor downhole flowing pressure on a gas lift installation, both either tubing flow or annular flow. And then you can also measure, again, pump intake and discharge pressure on a jet pump or a hydraulic pump.
Correct.
And one, that's typically the applications we see, right, is with some form of artificial lift.
Correct. We have seen also natural flow. Some customer wants to see, the pressure and, in natural flow, probably conventional reservoirs. You can see that that's another application outside of artificial lift.
Okay, so outside of artificial lift, you see applications where they're just simply monitoring static and flowing pressures on a naturally flow well. And I guess that brings up a good point. Another application that we work with a lot is for gas and CO2 injectors, where operator has a CO2 or a natural gas EOR project, and they're monitoring that injection pressure via the downhole gauge.
Yes, sir.
So yeah, guys, great question, and we'll discuss that in a lot more details in the application stage.
Yeah.
So Juan, you were talking about the calibration, right? And this is where you're putting the gauge at temperature, at pressure, in basically what looks like an oven, right? And this is what you talk about from the calibration piece, making sure that if we do see 1,000 PSI, that the gauge is actually reading 1,000 PSI. Is that correct?
Yeah, basically, well, first, just to explain what you have in the slide there and in your screen is the calibration certificate that basically shows the different step of pressure and temperature that the gauge went through.
So we have pressure down here on this axis, and then over here is that
the error in percentage of full scale.
Okay, and then each one of these lines are representing a different temperature.
Temperature and pressures, different points too. So you can see, if we were applying, let's say, for example, 3,000 PSI at a specific temperature, then you can see what was the value that the gauge was having at that precise moment with that temperature and pressure.
And that range there, that's going to be your accuracy range, right? So 3,000 PSI ranging from 25 degrees Celsius up to 150 degrees Celsius. That's your operating window based off of the pressure rating.
Correct. That will be your accuracy basically at that level, at that point.
Okay, perfect. And for anybody that isn't familiar with the metric system, we might have to break out the conversion to convert that over. But typically when we see on the high end of 150 degrees Celsius,
it's 302 F.
Fahrenheit. Okay. All right. You have to dumb it down for us Americans without the knowledge of the metric system. So, okay. That's good to hear. And so that's important, right? Is that, temperatures aren't going to vary much from reservoir to reservoir or well to well, but I guess from reservoir to reservoir, if you look at an Eagle Ford well, they're going to be closer to that 150 C. Whereas you look at, say, like a Permian Basin well, it's going to, I don't know what the number is, let's just say 75 C, right? But it's going to be significantly lower in temperature. And so looking at this calibration scale, understanding your reservoir temperature, your environmental temperature, is important to know, right?
Yeah.
Okay. That's good to hear. So Juan, we looked at the gauge, the piece that's actually measuring that pressure, temperature, and vibration that you mentioned. What are we looking at here? So we have our cable head and our splice cap.
Yes, yes, we review so far the gauge only. However, we need to power that gauge, and we need to allow the gauge or provide a pathway for that power to come to the gauge, also to communicate that data back to surface, to the surface computer. So in order for us to do that, we have to use the downhole cable, or TEC, totally enclosed conductor, okay? In order to connect that downhole cable to the gauge, we have to have a termination that is called cable head adapter termination.
And that's this piece here.
Correct.
Yep. And then I'll jump to the next slide, Juan, while we're talking about that, and we can look at those individual components. So this is connecting the tech cable, the TEC cable, to the downhole gauge.
Okay, here, this is the cable head adapter. This is my electromechanical connection to, to the gauge, or between the downhole cable, which is this one, and the gauge. So here I have the gauge, and then basically what we do is we screw the gauge into this connection, okay?
So that screws into the cable head,
Yes.
and that's connecting the gauge to the tech cable, which we'll talk about here in the next slide, but the tech cable is what tethers that gauge to surface.
Yeah. So here, then we finish, and we torque this to spec. And here you see a little hole here.
Yeah.
Once we torque and we energize the metal seal here, we pressure test to verify integrity of the seal. Okay, so we make sure by pressure testing that the seal is doing what it's supposed to.
Because you don't want to leak at that connection, because if you get any kind of water or formation fluids in there, electronics don't like fluids, right?
No.
And you could risk shorting the gauge out if you had a leak.
Correct. So you pressure test this connection here, but when you make this cable head adapter to the TEC, you pressure test second set of metal seals right here and this hole. Okay?
And same thing is to prevent that fluid intrusion. What do you typically pressure test that cable head to?
We normally pressure testing is project specific. It depends. Okay. It depends where you basically are going to deploy the gauge system. Normally, you want to be above the pressure where the gauge, where all the connections are going to be exposed. However, for our US operation, because that varies a lot, then we pressure test typically to 9,000 PSI.
Okay, and if we just use the example well of say 10,000 feet, you're going to be roughly around 5,000 PSI of hydrostatic at that depth. So you're pressure testing above what the probably environmental pressure would be.
Correct.
Once the gauge is downhole.
Correct.
Okay.
Yes. You want to make sure all the seals are functional at higher pressure.
Okay, that makes sense. And so that's the cable head, and so that attaches the cable head to the gauge itself and communicates that tech cable to the gauge.
Yes, and here we have what we call the cable to cable splice. The downhole cable goes from the gauge all the way to surface in parallel to your production tube.
So in like a 10,000 foot well example, you would have 10,000 feet of tech cable run across that production tubing.
Yes, sir. And as we run in the whole thing, people could potentially make mistakes. We could potentially have issues like somebody not pulling the TEC aside and hitting it with a power tone, or the tool pusher or rig operator closing the slips, before we pull the cable away.
Physically damaging that tech cable.
Yes. When things like that occur, in order to avoid pulling, and starting over the installation, you have to have any way, a particular way to repair that cable. In order to do that, we have developed this splice kit that essentially allows that repair.
Okay. And so that connects two damaged pieces of tech cable. If they're damaged on the rig floor, you cut that bad piece out and then you can reconnect it using the splice.
Correct. You electrically connect the conductor here, and you actually reestablish the armor integrity with these mechanical parts. These are metal to metal seals and are fully pressure testable, as you can see here in this hole.
Just like the cable head.
Correct.
Okay.
Exactly. So, and this is very similar design that we have with the cable head too. So it's very similar because we want to have repeatability, because the guys will have to do a cable head every time or no splice kit every time.
I see. Yes, Robert.
So a quick question. What are the most common gauge failure modes? And is that point where the tech adapter is a possible failure spot?
Yeah, that's a good question. So what is a common failure mode that you would see with the downhole gauge?
Well, that's a very important question.
So Juan, not to interrupt, we have a running joke of those answers is it depends.
It depends.
It depends.
It depends, but I would say that we at Flowco, we haven't seen many issues with the cable head adapter connection. We haven't seen, I would say, nothing. Okay, so
Because it's pressure testable, you would
pressure
find
testable.
that failure before you even run it in the
Yes.
hole.
yes, we have few failures, but the failure was not related to the installation or to the equipment. We have experienced issues where atmospheric discharges hit the nearby location and hits electrically all the components on the well pad.
Okay.
Yeah.
Yeah, and we see that in like West Texas a lot. So you're saying like lightning strikes, where you get that voltage spike and it burns up it. And I'll add to that too. Another thing that we've run into in the past is actually welding. So roustabout or something like that, welding on say like flow line or some kind of surface equipment, and it's not properly grounded. And same thing as you get that voltage spike and burns up the gauge that way.
Correct. Another point that is important is the integrity of the downhole cable. We haven't seen, like I mentioned before, we haven't seen issues with the cable head adapter connection allowing any wellbore fluid getting into the gauge. But we have seen a couple cases where the TEC actually midway was caught or reached.
Okay.
And it was because probably the well was a little bit more deviated than expected and caused, that potential.
And you get some like mechanical damage to the tech cable. Okay.
Correct.
Perfect. Yeah, and here in a few slides we'll show that tech cable and what that looks like and how that could possibly get damaged. So that's good. So Juan, we've talked about the gauge, how we connect that tech cable to the gauge. But this slide here shows, how do we get that gauge connected to the tubing, right?
Yes. So essentially, well, when I was going ahead of myself initially in the presentation, we were talking that this connection right here of the gauge, okay, connects to the lock on the gauge carrier, okay. If you're gonna do tubing sensing measurement, you don't need the annular adapter. You just run it straight to the gauge carrier, okay. And essentially after that, if you want to do annular sensing, then you use the adapter in the middle between the gauge carrier and the gauge, and you can sense, the annular pressure. Okay, but the gauge carrier is what allow us to install the system as a part of the production string, basically.
And so this anchors the gauge to the production tubing and either allows internal tubing pressure or external annular pressure readings based off of the application, right?
Correct.
Yeah. And these are going to be set for the same tubing size, grade, and thread connection.
Correct.
Just like your production.
Now, base material we carry is P110 due to the pressure rating of 10,000 PSI, but we have different other materials that, are available upon request.
Right. Yeah. Just like your production tubing, you would say. That makes sense. And so, okay, so we have the gauge, we have the cable head, we have the mandrel, which houses it. Now, the big question is, how do we get that gauge data up to surface?
Correct. So we use what we call the downhole cable, essentially. The downhole cable is, I have a sample, I brought a sample here, so I thought it was easier for us to go through it with the samples. So,
Yeah, I'm impressed. You're the first one that brought samples to us.
so
I'm waiting for somebody to bring me donuts. That's what I'm next.
next time. So in the US operations, we have multiple flavors of cable, right? Depends on the application and also the economics from the customer side too. So this version that you guys can see here is a bare, is what we call bare cable, bare TEC. Essentially doesn't have any encapsulation like those two have, okay? So
That's what the yellow is. That's encapsulation.
this is encapsulation.
Okay.
So essentially, this is for an application where the well is not highly deviated,
Mhm.
is inclination is very small, and you guys are, we don't want to set the gauge into the heel of the well. We want to be probably a little bit above the heel.
Mhm.
Okay. So in those circumstances, bare TEC would actually work okay in majority of the cases. Okay. Now let's talk about when it's highly deviated. If it's highly deviated, you want to have an extra layer of protection over this armor right here. Let's remember, this 1/4-inch armor of tubing is what maintains the electrical integrity of the gauge system.
Hey, Juan, what is the OD of this bare tech cable?
This is 1/4-inch, 1/4-inch OD.
Okay, 1/4-inch OD is that?
Point 0.25.
Okay.
So the encapsulation basically protects, it's an extra layer of protection over this armor. Believe it or not, this material is hard, and when you have a mechanical impact, it absorbs the energy of that impact substantially.
Mhm.
So it reduces the impact on the armor of the cable
So
itself.
it's like a sacrificial protection.
Correct.
Okay.
Correct. Also for abrasion, if you're gonna run these in, let's say, a rod pump, you're not sure if the tubing anchor is holding the tubing properly, and you would expect some movement back and forth, then probably having the encapsulation would be a good idea.
Yeah,
So that's a good point to answer this question. How exactly is this installed in the well, this cable?
oh, good question. And actually, to answer that, I'll jump ahead a couple slides, Robert, so we can illustrate that, and then we can come back to the tech cable. But yeah, that's a good question there. So I'm going to jump ahead a couple slides to answer that. So two of the installation methods, and this is across the board for any type of artificial lift or natural flow well, is either what we call an external or permanent installation.
Yeah.
And so in this case, the tech cable, which again is the biggest component of the downhole gauge system, right, is physically attached to the outside of the tubing.
Correct.
Either through bands or tubing clamps. And so that tech cable is physically attached to the outside of the production tubing.
Correct.
And it's run with the workover rig, right?
Correct.
As the rig's lowering the tubing, the tech cable's being physically attached to that tubing as it goes down.
Correct.
And that's probably the most common application, right?
That's how you can see it here in this top picture, right?
Yeah. Yeah, here you go. So here's your mandrel and the bands holding that tech cable to the outside of the tube. And here you can see the production tube and the tech cable being attached.
Yeah. So one point there, you can see also that the top picture shows a bare cable with probably a 2/7/8 tubing, and that one is encapsulated and appears to be a 3.5 tubing size.
Okay.
So
Okay.
you see the difference between the two applications right there. In that one, it was safe to run the bare cable, and in the bottom one, the customer decided, no, I want to have extra extra protection. So they decided to basically run with the encapsulated.
Okay, that's a good point. And to add to this too, one of the other installation methods is what we call internal or semi-permanent.
Yes, sir.
Where the tech cable can actually be run down the inside of the production tubing.
Correct.
And essentially hangs off its surface through a surface lubricator. And then so that tech cable and the gauge is just freely sitting on the inside of the production tubing.
So a follow-up, would you consider one installation method to be superior to one of the others?
Oh man, really good questions today. I'll give my input and
Yeah.
Juan, you give yours. Not necessarily superior to one or the other. I like the internal application for the ease of removal or change,
Yeah.
meaning that with the internal installation, you don't need a workover rig.
Correct.
If you need to remove the gauge, maybe to repair it or move it to another well, it's a very temporary solution to where you can pull it out and go allocate those assets to another well.
Correct.
If you need to get the data. The external one, in my opinion, is probably the better choice when you have either higher flow rates or maybe more corrosive environment,
Yeah.
right? Because the gauge is usually going to be protected with a production packer. So it's going to be more of a static condition or environment. One of the drawbacks, I guess you could say, to the external gauge is if you ever need to change the gauge or the tech cable, you have to get a rig to physically pull the tubing out since it's connected to the production tubing.
Correct.
Yeah.
Yeah. If the customer has a well already and they didn't consider a downhole gauge system when they were running the pipe or the production tubing, and then later they discover that it would be a good idea to have some downhole data, they can actually go there and just with our unit that is in the top picture right there, we can deploy a gauge system internally to the production.
Yeah, so you can go and install it after the fact.
Correct.
Yep. Good point there. Yeah, so really good questions, guys. So one of the things I'm going to go back a slide here is once we have the gauge connected to the cable head connected to the tech cable, and the tech cable ran all the way to surface. So we have the downhole components assembled, right? How and what do we need to do from that point to be able to, data collect that pressure, temperature, and vibration, and then be able to view it either locally at the well site or remotely through like a SCADA system?
Correct. Yeah, in order to get the downhole data, two things have to happen. First, we have to power up the gauge.
Okay, so we need to have power at the well site.
Correct.
Okay.
And you have to provide the power, and also you have to provide a means or interface to interact with the gauge data. And that's achieved by the surface computer.
Okay.
So the surface computer has the interface and the capabilities to power up the downhole gauge system. As controls and monitors the electrical stability of the system, and also reads the gauge, store data locally, and also transmit that data if the customer requires it to the SCADA system. So essentially interrogates the gauge back and forth. Okay, power the gauge and ask the gauge, hey, give me pressure, temperature, and vibration. And the computer defines if they want that data every second, every 2 seconds, every 5 minutes, every 3 minutes, every hour. And that information is pulled into the computer's memory, and then is available there for the SCADA from the customer side to pull that information to that server or to that system.
Okay. And what is the power requirements for one of these gauges?
24 volts.
24 volt is the
DC,
power system.
yeah.
Okay. And you mentioned that you need to have that interface card for the gauge connect to its surface, and then that surface computer. And is that surface computer data logging that information, because a lot of times we see SCADA systems lose communications, right? Maybe we lose power to a radio, or maybe the cell modem goes down or something like that. There's still a way to locally collect that information. So if you lose comms, you don't lose the visibility of the gauge. Is that right?
Correct. So the surface computer will actually keep data locally. Okay, if the customer wants that. Some customers, they don't like that idea, and they just want to have SCADA communication. Okay, but if the customer wants, we have the capability to record data locally. If the SCADA system, the communication in between, actually breaks down during a critical phase of a test that the engineer is performing in that well, they can always send somebody or drive to location and download the information from the computer.
Directly from the computer. Okay.
Correct.
And with that, do you need to have that interface card and computer for every single gauge? Because a lot of times we'll see pad applications where they have multiple gauges on a pad. Do you have to have that individual interface card and computer for each one of the gauges?
The short answer to that is no. If you have a well pad with 4 or 6 Flowco downhole gauge systems, we can always, configure one computer for all those wells. So they can actually power up all those wells and also pull the data from all those wells, and store the data and transmit the data of all those wells with a single computer to their SCADA system.
Oh, that's nice. So you can reduce your footprint and tie multiple gauges into one system.
Correct.
Okay. Yeah, that's good to know. Perfect. Thank you, Juan. So we talked about installation methods, right? Externally or internally, both achieving the same point, right? Is that we're putting the gauge at the bottom of the artificial lift system, at the bottom of the tubing string, to be able to collect either that tubing annular pressure and temperature or that tubing pressure.
Yeah.
And again, one thing mentioned too is, depending on the artificial lift types, you would pick your different installation methods. Like if you had a sucker rod pump or a PC pump, of course you'd have to go external installations, right? Because you're going to have your rods and your pump internally.
Correct.
But if you had a natural flow or a EOR injector project, or even a gas lift, you could pick between external or internal based off well environments and applications.
Correct.
Yeah,
that's absolutely correct.
Okay, perfect. Thank you, Juan. So Juan, with time, I want to switch to those applications that we've been talking about, right?
Okay.
The applications and how we can use that data from a production standpoint. And so here we kind of listed our most common applications, right, with the downhole gauge. And of course, a big one's gas lift. And in my opinion, from a gas lift side, this one has been a game changer, because when I look at artificial lift, I'll tell you, I get envious of ESPs, right, electric submersible pumps, because they collect so much data on the well. You have temperature, you have pressure, you have vibration, you have hertz, you have all this data that an ESP is capable of collecting and transmitting out, right? Well, as when we put a gas lift system on, we have tubing pressure, casing pressure, and injection rate. And so we lose that downhole visibility. And in my opinion, that's been a big application, is actually seeing what your flow and bottom hole pressures and temperatures are when you have a gas lift system.
Correct.
Of course, another big one is any kind of pump application, jet pump or hydraulic pump, rod pump, and PC pumps. You can get that pump discharge or intake pressure, right? So you can monitor, maybe we need to adjust strokes per minute on a sucker rod pump, or maybe we need to adjust the hertz on the surface pump for a jet pump based off of that intake pressure, just like your PIP would be for ESP.
Correct.
And then for PC pumps, you actually go a step further than that, right? So you get that intake pressure, but typically, what are the other things that you see operators monitoring, especially with like rod pump and PC pump?
For PC pumps, operators basically try to understand the performance of the pump
Mhm.
and trying to diagnose earlier any potential issues with the pump. Okay, so what they do is they monitor the pump intake pressure. That's critical for a
Yeah.
PC pump. The discharge pressure too.
Mhm.
Okay, they want to know the differential pressure through the pump.
Right.
Okay, and also vibration.
Okay.
So, for instance, some customers in the past, they basically use that downhole vibration information to learn, over different cases that they discovered over time. They see what vibration was tied to a particular issue. For instance, there was a lot of gas going through the pump. The vibration is different.
Mhm.
Okay, the elastomer of the pump is breaking in pieces. There is a different level of vibration there. So they ran some characterization of those issues with that data, and they were able to see when basically a pump was to start to give up, or there was a lot of gas and stuff like that. So start adjusting and preventing issues, or if the issue was not preventable, then, a scheduled rig intervention with time, so
Mhm.
they don't actually have a lot of deferred production because
Okay.
the well is down.
Yeah, that makes sense. So in your pump applications, you can use that vibration piece of the gauge to recognize essentially how efficient your pump's running.
Correct.
And that's really helpful. And that's kind of what this slide represents, right? Is that you can use that gauge, of course, from a reservoir monitoring standpoint, but again, from a production side, we can use that to optimize our artificial lift if it's pump or gas lift or EOR injection.
Yeah.
And then, like you mentioned, you can help kind of diagnose some of those problems. And here's where we'll get into some of those details, right? Especially with gas lift optimization. If we have a downhole gauge in the well, what can we use that gauge for outside of the reservoir side? So from an optimization or from a controlling of an artificial lift system. And so it gives us that real-time bottom hole pressure and temperature to help us do a couple things, right?
Yeah.
Of course, with any kind of artificial lift, we can use it to optimize, meaning that if we increase strokes per minute, if we adjust injection rates for gas lift or EOR, or if we reduce surface pressures and we see a reduction in bottom hole pressure, then that tells us that we're increasing that drawdown. That increase in drawdown should hence give us more production, right?
Correct.
Another thing that we can use, like you mentioned, is the troubleshooting piece. If we see vibration increasing on pump applications, then that maybe tells us, hey, we have gas interference, or we just have wear on the pump and maybe it's time to change it out.
Yeah.
From a gas lift standpoint, if we see a increase in bottom hole pressure, then that can tell us that maybe we've developed a hole in the tubing, or maybe we have a bad gas lift valve and our lift point has changed, and that has negatively affected our system by increasing our bottom hole pressure.
Correct.
So we can monitor that vibration and pressure to really understand the health of our artificial lift system.
Correct.
So, and here we have a couple examples of looking at that downhole pressure to understand the system. And this is a pretty simple one, right? This is just pressures in blue and productions in orange, but this is just simply a drawdown monitoring, right? We start up the gas lift system here. Of course, maybe we had some issues here, compressor went down or something like that, but we're able to draw the well down and then kind of get that bottom hole pressure in that stable, maintaining flowing bottom hole pressure. Another one that I like here is identifying instability issues. Maybe we're not injecting enough gas. We have something that's causing the well to do two things, right? It's keeping a high flow and bottom hole pressure, and the min max changes in flow and bottom hole pressure, that delta is relatively large, meaning that we're inducing a lot of instability, slugging in the well.
Correct.
And so for me, from a gas flow standpoint, that tells me, hey, we need to adjust injection rate. In this case, we need to increase injection rate because we're experiencing liquid loading. And by doing that, we're able to draw the well down, lower that flow and bottom hole pressure, and more importantly, reduce that delta P between those slug frequencies.
Correct.
And so here we can see pre-optimization to post-optimization just simply by increasing or adjusting our injection rate, that we're able to draw the well down and then minimize some of that liquid holdup or liquid loading.
Correct. And on top of that, I would add that we increase production because we decrease the downhole pressure.
Yep, good point. And so by reducing that flow and bottom hole pressure, we should get a increase in our liquid production.
Correct.
Yeah, good point. And here's another one that outside of kind of artificial lift, right? This is more on the pressure monitoring side, is using the gauge for buildups or offset frac interference. And so in this case, we had a shut-in, relatively long shut-in, about 30-day shut-in, and we get to see that pressure change and that slope or the pressure build from a flowing condition to a static condition over time. And then once we, open the well back up or start up the artificial lift system, that drawdown and trend back to, maybe where it was previously, and things like that. So in this case, we get to see that bottom hole pressure change when we go from a flowing state to a static or shut-in state.
Correct.
Yeah. And of course, when we get into troubleshooting, we can use it as well. And like you mentioned with the vibration or change in pump discharge or intake pressure, we can also see the same thing from a gas flow side, right? Is that bottom hole pressure in blue, surface pressure in green, we see an increase in our bottom hole pressure, and it's due to that increase in surface pressure.
Yeah.
So maybe compression went down, or well was choked back, causing that change in bottom hole pressure. And in this case, it was induced because of some kind of surface pressure change.
Correct.
And then another one that I see that can be helpful to identify, especially if you have like infill or feed-in issues, is excessive drawdown on the well, right?
Yeah.
And so here, this example, we started at pretty high bottom hole pressure. And as the well was turned on, the bottom hole pressure decreased and continued to decrease and actually dropped way down to like 200 PSI bottom hole pressure. And so for me, that says, hey, that's a pretty excessive drawdown starting at roughly 4,500 PSI and pulling the well down to like 200 PSI in a matter of a few days. And so in this case, what we find is that we actually had a bridge or a plug that was preventing formation fluids and pressure to enter the tubing. So in this case, basically the tubing and casing had been completely evacuated of all its fluids, showing that low flow and bottom hole pressure. And so in a case like this, maybe we need to do an intervention, go pump an acid job or a flush to try to dislodge that plug, or possibly have to like pull tubing and go physically do like a clean out to remove that plug. So really helpful information to see based off of things like our bottom hole pressure, our vibration, any of that data that we're collecting with a gauge downhole.
Correct.
Yeah. So really good information to see, Juan, and trying to kind of wrap up our presentation today and open the discussion up for some questions and answers and get your opinion and feedback off of your experience. Before we do that, real quick, just update everybody. We have two more before we wrap up this year's e-learning series. Next month is going to be Plunge Lift 102. It's going to be more in depth plunger lift optimization and troubleshooting presentation, technical presentation focused on how to optimize and troubleshoot plunger lift systems. And then we'll wrap up our e-learning series this year with plunger assisted gas lift. Again, more focused on well selection, how to optimize, how to adjust a system that is on plunger assisted gas lift.
Perfect.
But Juan, with that, you ready for some tough questions?
Well, I guess
All right.
I'll try my best.
Perfect. Well, thank you. I'll stop sharing this and we'll jump to Juan and we'll throw some good questions at you. So Juan, I have to say we got a lot of questions from the audience on this one.
Okay.
So that's really good. That's encouraging to see. And I'll start with a couple of them here. Okay, so one of the questions asked, and this probably goes more to that surface control standpoint, is what frequency do you typically see the gauge refresh or collect that data? Is there a min and max like data acquisition time frame for these gauges?
Yeah, I mean, the minimum we can collect data from the gauge is 1 second.
Okay.
And that means that if you have 6 wells connected to that surface computer, you can pull 1 second on all those wells. There is no limitation. So if you have 6 wells or you have 16 wells, you have 8 wells, you can pull 1 second data all the time. There is no condition for that. And the maximum is hour, 15 minutes, you know, it basically put 3 hours, 5 hours, 24 hours, whatever you want in the max side. There's no limitation.
But typically it's probably better to at least locally pull that gauge at a higher frequency and allow the operator SCADA system to pull it at whatever frequency they want to see it.
Yeah. I mean, if they want to have a fail safe there, yes, 1 second will be perfectly fine.
Okay.
But just be aware when you reach the maximum memory, it start overriding the oldest file.
Okay. So it doesn't stop saving, it just overrides the previous data.
It will record all the data until the memory is full, and it's going to start overriding the oldest file.
Okay. Oh, good. Hey, and Juan, I got another question that goes back to the tech cable. So you mentioned that bare tech cable is 0.25 inches, quarter inch. What's the OD of the encapsulated tech cable? It looks bigger than your quarter.
This one right here is 11 by 11 millimeters. This is
here. We can put it right there so everybody can see it.
All right. So, yeah, and the way we have it in our tech sheet and everything is by millimeters. So this is 11 by 11.
So you have to convert that for us.
Yeah. So
I think it's 0.4 inches, correct?
Yeah.
11 millimeters.
Yeah.
So it is bigger, but it's not, extremely big to where you wouldn't be able to fit that to the outside of your production.
Correct. No, it's not that big. It's just a little bit bigger, just to protect the armor of the T's.
Okay, so your bare cable is going to be a quarter of an inch, 0.25.
0.25.
And then this is roughly going to be 0.40 inches.
Roughly. Yeah.
Okay. Okay.
And maybe I missed it, but what was the difference between these two?
Okay. So that's a good question, right there. So we have these 3 samples, and we were talking, in general about the armor encapsulation, the insulation here, but also the conductor. Here you can see that these 2 is an 18 gauge 7-strand conductor. Okay, it's flexible. It's more flexible. Okay, and you have those, let's say, mini wire in there. You have 7. In this case, this is 16 gauge conductor. This is stiff. It doesn't move as much. Okay, so these are the 2 versions we typically see for downhole cable. However, here at Flowco, we prefer to use the 18 gauge conductor. Okay, because it's more flexible, so it's more forgiving with vibration, and also in one of these little wired breaks, you have 6 or 5 more holding that electrical connection to the gauge. Whereas the 16 gauge is just one wire. If this breaks, then you have no electrical connection with the gauge. Okay, so that's the reason why we prefer here at Flowco using the 18 gauge 7-strand tin coated conductor.
Okay, that's a good point, Juan. And so what you're mentioning is this is one solid conductor like you would see electrical wire in your house, whereas this one is multiple strand
Yes.
wire. Okay, yeah, that's a good point. Thank you, Juan. Got a couple other questions for you, and this might be a joint question here. One of the questions was asked, have we ever encountered the tech cable breaking on a internal installation to where the tech cable is installed inside of the production tubing?
That I can recall at this point, no. I just wanted to highlight that when we go and we do, we talk to our customer for internal deployment of a gauge system. What we do is we request some well data. So we use a system to kind of simulate the installation, and we can see there where the maximum, the minimum, how far we can reach, et cetera, et cetera.
Yeah, like a load and drag calculation.
Correct.
Okay.
So in that way, we can actually verify that we can achieve what the customer is requesting, minimizing any potential risk associated to breaking the TEC.
Yeah,
okay?
That makes sense. And I'll add to that too, Juan. I've not seen the tech cable break downhole, but what I have seen is it gets cut at surface because it is running across a master valve in the wellhead. And I have seen where the master valve essentially gets shut by accident, and physically shears the tech cable. Usually at that point, the operator will have slick line or braided line come out there and go in with an overshot and fish the tech cable and pull that tech cable back up to surface, where at that point they can check the connection, redress it, and remake that connection.
Correct. Okay.
Yeah. So perfect.
Good point.
Juan, I have one more question for you. For the gauge itself, what's the difference between a piezo and a quartz gauge? That's a question that we see quite a bit. Is there a difference? What's the high level?
Yeah, the quartz gauge uses a quartz crystal transducer, and it gives you is more accurate and give you better resolution. So
in the 0.05 that we see.
Correct.
Okay.
So I don't have a number in my mind, but the beauty of the quartz gauge is if you want to do reservoir interference, okay, and you have a well there, and you have a monitor well, and you have multiple wells there, and you want to see if this well is interfering with any of these wells, the resolution helps you to pick that change faster than a piezo-resistive with a smaller resolution, because the quartz will actually peak as the smallest variation in pressure quicker than the piezo-resistive.
Okay. And so some operators would want a higher resolution than 5 psi.
Than 0.05 psi, probably in some cases they would, because they want to make sure they don't want to have. In reality, the engineer doesn't want to have wells closed for too long. Okay, so that's the reason why they prefer using quartz, because they can pick that change or that variation in pressure faster, because it has a very fine resolution.
Okay.
It's useful for PTA testing.
Okay.
Sure.
All right. Perfect. Good. Thank you, Juan. Well, guys, we're getting close to our time here. So want to thank everybody for joining. Definitely want to thank Juan for his input and his experience and really taking the time to share that. I think we have one more question before we wrap up.
Last minute question. When running these for long-term monitoring externally on production tubing, do you recommend banding or clamping? Pros and cons of both.
Oh, wow. That is a good.
That's a really good question.
Yeah.
Well, you want to start?
I can start if you like. And so personally, I like the clamps, the upset clamps, and the way the clamps work is they connect the cap or the tech cable, excuse me, across the upset of the production tubing. And they do two things. They kind of act as a centralizer because the OD of the clamp's larger than your production tubing, meaning that when the tubing touches the wall of the casing, the clamp's physically touching the wall of the casing and not the production tubing or the tech cable. A secondary benefit that we've found mainly through operational experience is the clamps don't break when engaged in high deviation. The bands tend to break when the tubing bounces back and forth and hits the ID of the casing wall. And so what happens when those bands break off, they fall down to the bottom of the tubing or the top of the pack or the top of a liner and things like that. And they do make fishing very difficult. So personally, for operation, for fishing, and for really the reliability of the gauge and the tech cable, I prefer clamps. One other thing to add to before I let you provide your input is the clamps are reusable. So when you pull them out of the well, you essentially clean them up, right, inspect them for cracks or damage, and then you can run them on the same well or an offset well. So it's an asset, it's a piece of equipment that you can reuse multiple times, whereas your bands are a one-time use application.
Correct. I agree with you. The only thing I would add is it depends on well geometry also and economics. So
good point.
So basically, we'll come down to that.
So to add to that, before we wrap up, like when you talk about well geometry, is what do you typically look for inclination, where you'd prefer to run clamps over bands?
I would say inclinations. It depends on the tubing size too. It depends the casing size, because if it's a very heavy pipe. Then if it's 2/3/8, I wouldn't worry too much with 10 degrees inclination.
Okay. So say 10 degrees or more is where you'd prefer to see clamps.
Correct. I would say.
Good. Well, hey guys, we wrapping up this. Juan, again, thank you very much for joining and providing that insight. Thanks for bringing goodies. That was nice to be able to show everybody attending that, and everybody that was able to join. Thanks for getting on, and we do appreciate it.
Thanks.
Thank you guys. See you next time.